Welcome to this session of Shadow the Scientist, Astronomy Night at the International Gemini Observatory North. My name is Jamika Marshall, and I am pleased to serve as the Shadow the Scientist Coordinator. Shadow the Scientist is an initiative housed under the Creating Equity in STEAM umbrella of programs offered by a team at the University of California, Santa Cruz. Now, we'd like to extend a very special welcome to the teachers and students of Modern High School International. Aloha. With us this evening for this session is the Shadow the Scientist founder, Raja Guhathakartha, who is a distinguished professor of astronomy and astrophysics at the University of California, Santa Cruz. Raja, would you like to share some remarks before we get started?
I'd be happy to. I see such a wonderful intersection today of so many things. So, Jamika, this just feels like many things coming together. I'll just list a few of those. As you know, Jamika, Brian and I go a very long way back. Brian was an undergraduate at UC Santa Cruz, and so he and I have known each other for a very long time. And I've known Modern High School, not international, but Modern High School, the other section of Modern High School, for just about as long, because my sister studied at Modern High School. My sister's daughter studied at Modern High School, and while my sister's daughter was studying there, I started collaboration with the school to talk about astronomy research there, and that has led us to this moment where, in the meantime, Modern High School has a whole new campus, which is a co-ed campus with the IB curriculum, and that's who's with us in the auditorium today. So thank you all for for making this all possible. Thanks to the Gemini North host. Thanks, Jamika, for putting this all together.
Wonderful. Fantastic. We're so glad you can be with us, Raja. And students and teachers, as I said before we got started, please feel free to drop your questions and comments in the chat. You can post them right there at any time. Okay, so a bit about Gemini. The International Gemini Observatory actually consists of twin 8.1 meter optical infrared telescopes, which are located on mountains in Hawaii, here on Maunakea, and Chile on Cerro Patron, which enables the telescopes to collectively access the entire sky. Gemini Observatory is unique in that it utilizes the Q observing mode, in which science staff take observations on behalf of science teams from all over the world. The staff determine the conditions on the ground and in the sky, as well as the scientific priorities, and then choose from a pool of scientific programs to observe. In this session, we have the privilege of shadowing the Gemini North observing team, which tonight consists of Brian Lameau and Denise Hong. Now, hosting with me this evening is Zachary Hartman and Leilani Losey. Welcome, Zach. Welcome, Leilani. Now, you will also be in for a very special treat, as we will be joined by some guests this evening, also the very beginning of our session. This is Emma and Haywan. Hi, Emma. and Hewan. Aloha to you both. Yes, I want to make sure I can see you. There you are, Hewan. Wonderful. Perfect. So Emma and Hewan will showcase the next exciting instrument that will be available to the Gemini North community early next year. And that's the second generation of the Immersion GRating INfraRed Spectrograph, IGRINS 2. Now, before we get to our very special guest, let me turn it over to Zach to get us started. Zach.
All right, sorry, we had to reorganize. So, hey everybody, welcome tonight. I'm just gonna jump into sharing my screen real fast. As I believe Jamaica's moving into here. And then we can get started. Okay, where is share screen? Here, share screen. All right, so this is what I want. All right, so hi everybody. So this is right now what we are looking at currently. We are actually looking at one of the brightest stars in the sky in the infrared.
Okay, Denise, we're ready to move on to 24A Q118, observation number 18. Sorry to interrupt, Zach.
No worries. And so, as you just heard, we're
Thank
doing
you.
live observing as we go. So if you hear people in the background, that is Brian and Denise talking about the observing that's going on right now. So currently, the observations we're taking are using a special spectrograph called a IFU, or integral field unit. And so what this does is you can kind of see this in the lower right of this image. You can see what appears to be a star. And the idea behind this integral field unit, and actually I'm going to turn it over to either Brian or Emma because they're the GNIRS instrument scientists. So does either one of you want to describe this, seeing as you've worked so hard on it?
Hi. So
Go for it, Emma.
I go, you're observing. While Brian is busy, I can take over now. So what you're actually seeing is a full 3D image of a part of the sky that is splitted on the plane. So the way you can see that is that you have on the left side, you see that there is like this dot. That's actually the reconstructed image. And every single slice of this image, horizontal slide, is actually contain a full spectrum. So what you're seeing is just going from the top to the bottom, the different spatial position of the object we are observing. As Zach mentioned, this is one of the brightest stars in the sky. That basically is around 0th magnitude, or that's actually how it looks like on the left.
So I'll just jump in for a second. So this was actually the telluric star that we took beforehand. So this was the calibrator. So we're now moving to the very bright star. So just to give a little bit of context there, Emma.
Okay, thanks.
So it's got to get brighter is what's
Yeah.
is what's
Got to
going
get brighter. Yep.
So we are observing a really bright star that we use to calibrate the tool. Is a way we let's say there are in the spectrum of every object, you don't only observe the emission from the source itself, but you see also the everything that comes through the sky, so the entire atmosphere. And the atmosphere has some absorption feature that if you want to remove, you have to observe first a star that you know perfectly how the intrinsic spectrum will be. And then you use that as a model to remove all the absorption atmosphere. And so that's what the first observation we were taking. And in this case, that rarely happen. Most of the time, you have a really long observation for your science targets because most of your science targets are really faint. And then you have what is a really short observation for your calibration star, the telluric star. But in this case, it's going almost to be the opposite because there are not that many stars that as bright. And so the time spent on the calibration is probably going as long as the time spent on the science itself. In addition, what Brian is going to do is actually to take, if condition allows it, is going to take more than one wavelengths. So it means that what astronomers call are in the infrared, they're called J, H, and K, that are 3 different wavelengths bands. One is a 1.1 micron, one is a 1.7, and one around 2.2 microns. And it's going to scan toward the system if it or the wavelengths. So at the end, you will have a full 3D information covering 3 different bands. Something else?
Yeah, and I think for this target in particular, what they're really looking for is any signs that this star that we believe to be single right now is actually a binary. And so they'll be looking at the different features that they see in the spectrum and looking for signs of binarity in the spectrum itself. And so hopefully we will see the bright star soon. But as we're just sitting here, I'm going to actually change the screen a little bit. And we're going to go to the screen. So Gemini has a lot of different screens. And so you just saw one and now you're seeing another one. And this one is showing what we call the TSD, which is the telescope systems display.
Intro filter for this one or
And so on this screen, you see a lot of information that's going on right now. So you see a diagram of the telescope and where it's pointing, along with this blue circle over here is the moon. And then you can also see on the middle, towards the middle right side, you see a telescope display of the light showing where it's going. And you can see right now that the light comes around the sky, hits our primary mirror, then goes to a secondary mirror and bounces down to where the instruments are, and then is being diverted into GNIRS. So that's the instrument that we're using right now. And then you see a lot of other different parameters that are going on with the telescope. And then we also have values for what our seeing is, although these are not current, I think, because we were just slewing. And basically seeing is a measure of how much atmospheric distortion there is. So for astronomers, we want that seeing to be as low as possible so that we can see the true image, not as much affected by the atmosphere above us. And so the lower the better for us. And right now it's pretty good. This is what we would call IQ 20 conditions. So very good seeing for us. And yeah, that's what we're doing currently. So I'm going to flip back to the other screen and turn it back over to Jamika.
All right. Thank you for getting us started and giving us a good feel for what's going on as we begin the session. So as I said in our welcome, we have several hosts here with us. In addition to Zach and our special guest there in the room with him, Emma and Hewan, we also have Leilani Losi. Leilani Losi is, of course, the Gemini staff here that manages the community education and engagement team, and she would like to share a few remarks. Welcome, Leilani.
Aloha, everyone. Mahalo nui for having me join as a guest tonight, and maybe myself or other education engagement team members will join more in the future. But in recognition of today being Earth Day, which I'm not sure if that's International Earth Day or really more of a national celebration, I just wanted to come on here and talk a little bit about the incredibly important and sacred place from which we conduct our science, which is Maunakea. So I have just a few slides to share with you to talk a little bit about how awesome Maunakea is, and then some of the very important work we engage in with our community to help take care of our Earth and of the land as a whole. So let me just share my screen here. Okay, got that open. And then let's go into slideshow. Okay, so as you're all hopefully very aware, you're joining us for Shadow the Scientist at Gemini North, and today is Earth Day. So I wanted to start us off with an Olelo no Eau, which is essentially a native Hawaiian proverb or saying or piece of wisdom that was passed down through many generations to us today. And so this Olelo no Eau says, Maunakea kuhivi kuha'o ikamalie, which means Maunakea stands alone in the calm. And because these are proverbial sayings, they're sayings of wisdom, they're also very full of like lots of different metaphors and understandings. So while there's a very clear interpretation of what this means, there's a few that I want to bring up now. So first of all, Native Hawaiian people, who are the indigenous people to this land, lived here for many generations and performed science through observations, right? So in living on the land, through observing all the different patterns and microclimates that exist within our islands, they were able to pass down knowledge of our different microclimates and of the things that they observe. So when it comes to Mauna Kea in particular, Mauna Kea is the largest mountain in the entire world when measured from the ocean floor. So from the very bottom of the ocean to its peak, it is the largest mountain mass in the whole world. And this does severely affect the weather patterns that we observe around the islands. And it's often thought that Mauna Kea protects us, protects the towns that surround it, especially Hilo, from really damaging storms. In the Pacific Ocean as a whole, there are islands and other parts of the ocean who suffer from very severe monsoon seasons and other tropical phenomena that are common to those areas. But in Hawaii, what we have observed in even the decades that we've had, like, you know, media communications and recordings of storms and things, we've seen a lot of what could be very damaging storms come towards our islands and then be redirected in another way. And so there's a lot of observational proof that Mauna Kea and Mauna Loa, which is right next to it and is the widest volcano in the world, help to contribute to these weather patterns that our elders knew and that we continue to witness today. In addition to that, Mauna Kea is, of course, one of the best places in the world to do astronomical research, as we are all observing live tonight. And this saying references that as well, and the very specific weather phenomena that we see every night, which is called an inversion layer. So every night, due to our placement in the middle of the ocean and our isolation within the ocean and the elevation of the mountain, we actually see most clouds that are above the summit of Mauna Kea, where the telescopes are, sink below the summit when it gets dark and cool. And so this is a phenomena that has been studied by the university even in recent times on both Mauna Kea and Haleakala. And that's a very unique feature to us. So Mauna Kea stands alone in the calm, in the midst of storms, in the midst of regular weather patterns, and it does a lot to protect us as human beings, but also to provide this gateway into the universe from which we are able to conduct our research. So that's what I wanted to bring today for Earth Day as the main part of our conversation. The other little bits that I'll leave you with is the idea of aloha aina. So I understand that for a lot of our sessions, we get lots of international people. And so mahalo nui to everyone for being here. If you haven't heard of aloha aina before, it's very much a concept that embraces Native Hawaiian value and way of life and how we engage with being inland and the almost familial and family relationship that we have with these islands. And so here is another Olelo no Eau, so another wisdom saying, proverbial saying, which is He ali'i ka'aina, he kauwa ke kane. So the land is chief and man its servant. And so, like I said, this is very much a reference to the fact that the land is where we come from. This is our like ancestral roots. And without it, without caring for the land, we could not continue to exist here as people. So while this is super critical being on islands where our resources are somewhat limited, this also stands to be true for our entire planet, right? We see a lot of things going on that we need to recognize on Earth Day and every day that speaks to how we need to care for the Earth. And lastly, just a little mention of what our staff here in Hawaii at the Gemini North Telescope have had the opportunities to engage in lately in order to do Aloha Aina, to be a part of the community and to take care of the Earth. Just a few things that we're really grateful to have been able to do all together is like fish pond restoration. So we have traditional native Hawaiian fish ponds here in our town where our base facility is, where everyone's doing their observations from the control room right now, just like a 20-minute drive away, yeah, are a whole bunch of fish ponds that have been cared for a very long time in a very traditional way. In a very sustainable way. And we could go on and on about fish ponds, but we won't. And so that's a really fun way to engage in what it means to take care of Aina. And then we also have had the opportunity to go and pull weeds up on Maunakea with the Center for Maunakea Stewardship. So when people go to the top of the mountain to the telescope, they have to stop midway in order to acclimate to the high elevation so that they don't get sick when they go all the way to the top. And at that mid-level elevation, there's a facility where astronomers from all the telescopes can go, and anyone who's going up to the summit would stop there and rest before going up. So every other month, we volunteer with lots of other people to take care of that area. We go and pull weeds from the surrounding land so that native plants can continue to grow. And lastly, I'll just mention the very important work of Maunakea reforestation. So you saw in that first picture with Olelo No'eau that Maunakea is massive. That's not even the whole mountain. That's just from the like Saddle Road elevation. And as I said, Maunakea goes all the way to the bottom of the ocean floor. But, you know, as a result, there's many parts of Maunakea to care for. And unfortunately, in our long history as human beings on this island, you know, we've done some things that now we're having to deal with. So for one, introducing goats to our land has severely impacted the native forests and the native birds that exist only on Maunakea at this point. And so while there's work being done to get rid of the goats, we also now are having to replant a lot of the forest so that the birds who exist only on Maunakea, known as Palila, don't go completely extinct. And we're kind of like in critical time right now for saving the Palila. At this point, the public record shows that there's only, gosh, I don't want to get this number wrong because it's a crazy number, but I think it's down to 300 birds, which is essentially extinction level event, in which if something dramatic is not done in the next 2 years, like these birds will be extinct within the next 5. And so we've seen this across the Hawaiian Islands. We're called the extinction capital of the world, in fact, because before people came here, there were so many native species that were able to evolve and grow. And once we came with all of our different introduced things, we kind of interrupted that ecosystem. And so we're doing what we can to save these really special places and these special birds. But it takes everyone, including all of our astronomers, all of our community, all of our families, to just do what we can. So that's it for me. Mahalo nui for listening, and happy Earth Day, everyone.
Thank you so much, Leilani, for sharing that those amazing cultural insights. I certainly did not know that the Palila bird was so endangered. And as we've both had the privilege of working together at another place on Maunakea, I've seen Palila birds, and I knew that they needed to certainly be protected years ago. And I just assumed that conservation was moving ahead. So it's good to know that there's still lots that we can do. Thank you so much. And yes, in the chat, thank you, Brian. If you all have any questions about Maunakea, about Earth Day, or anything that you've seen so far, please, teachers and students and everyone else who's joined us in the chat, please post those at any time right there in the chat, and we will get to them. Thank you so much. All right, so now let's first go to Raja, then we'll check back in with Zach, and maybe chat with our other special guests, Emma and Hewan. Raja.
I just wanted to add one thing that Leilani, first of all, that was just beautiful, and it reminded me of something very, very special many years ago when we were early in our relationship with Modern High School. Not Modern High School International, but Modern High School, which is an all-girls school. At that time, Maunakea was hosting, I think through TMT, was hosting something called the Pacific Astronomy and Engineering Summit that would bring school students from all the TMT partner countries to Hawaii, physically to Hawaii, where students would learn about the mountain, about the project, present posters. So my students and I worked with 3 girls from Modern High School back then. They traveled all the way to Hawaii. Following year, to represent India. The year before that, there had been 3 boys from a school in Delhi who had represented India, and we had trained them too. And then 2 years in a row, two different groups of 3 high school students from Modern High School actually visited Maunakea. I think when I was talking about closing of the loop, this is, I'd forgotten to mention that.
That certainly does highlight the special relationship that you bring in connecting all of us through founding Shadow the Scientist. Okay, mahalo nui loa, Leilani. So let's head back over to Zach. Zach is with our other 2 special guests, and I see they're having to kind of shift and arrange themselves there to be in front of the monitor. Awesome. Zach, are Emma and Hewan ready to chat with us about this new instrument that's going to be tested soon?
No, we're not. I'm joking. So, hi everyone.
Emma, sorry, before you get started, I just wanted to jump in. So we are observing one of the brightest stars in the sky now. And in addition to doing many, many other things at the observatory, you and Hewan support both the instrument that we're using now and the scientific programs that we're observing. And in fact, Hewan is the primary contact scientist of the primary Gemini North staff that is involved with this program here. And so I just wanted to ask a quick question, colleague to colleague here. We're seeing some saturation. This star is very, very bright, and I think Zach just highlighted the screen, so it's not too bad, but there's reasonable saturation. So I just want to run by you. So currently we were doing 20 coads of 20 seconds. I'm going to vary that now to 40 coads of 10 seconds. Do you guys have any objections?
No, that sounds good. Thank you.
Okay. So please take it away.
Thanks. It was convenient actually that the contact scientist was here. So as
Thanks,
you may
Hewan.
know,
Thank you, Brian.
when we are observing, we like the particularity of this object that we actually didn't know how bright is this object in the sky, because that's a variable star. So we have a best guess within a factor of like 8, more or less. And it seems a lot, but it's really a lot. And things can go, if you have a light in front of you that is 10 times brighter than you expected, you can get blinded. As you can see in this image, the red part here is a sign for us that the object actually saturates, or in other words, reach the maximum level that the detector can contain. And so what Brian is doing is actually tweaking the exposure time to actually be there on the left. You can see it better. So just a little bit. So Brian is tweaking the exposure time to make sure that we don't have that effect, because there is absolutely no information. Once the detector reach the maximum count that it can detect, there is no information left. And so we have to drop the exposure time and go there. So abandoning this side of the project, we can go back to
No. You had it set up correctly.
So just to do a step back to understand why everyone at Gemini North is super excited about these things, is that we don't have that many new instruments coming online. It's not something that is like, yeah, you can see that it's like changing your car. Like when you have a new car, you're excited, you want to try your two things, but it's not only changing your car, it's actually like completely changing way of transportation. So it's like you're used to drive a car, and at a certain point, someone gives you a new boat, and you are extremely excited. And that's happened on the time scale you may consider to change your car. So it's like the order between 5 and 10 years, we have a new instrument here. So this is a unique situation we are now. So this is iGreens 2. Me and Yuan, we are working on this to have this fully integrated with the telescope. And there are a lot of people that are working on this. It's not a 2 people effort. It's like hundreds of people effort. And one of these people is Zach here. He also helping in that. So what the instrument do is actually work again in the infrared, and it's only a spectrograph. That means that you have allowed you to disperse the light in the different colors of the rainbow. And the particularity of this object is that it has only one single observing mode, but it does this in a spectacular way. So the way that some instruments work, they try to be like as a Swiss knife. So you can do a lot of things with the same instrument, but then introduce more mirror, more reflecting surfaces, more mechanism that need to move, and then like cause a little bit of jiggling between different things. And every time you add a mirror, you lose throughput. And so you have like, you lose your sensitivity on the instrument. While this specific instrument, you have a single slit, a single grating, a single, 2 detectors actually. And it does everything in like, you cannot choose anything else. That is how long you're going to expose in the sky. What you see on this image is actually the first light of this instrument. That is the first time it's been brought to Maunakea, and the first time it was being attached to the telescope. And this is one of the first, well, actually, this is the real first images we have taken. You see that there are actually 2 images, one on the left, one on the right, because the way the instrument works is that the light got split by a mirror that's semi-reflective. It means that one side, the light got the light above certain wavelength will push on one direction, and the light on the other or below a certain wavelength got pushed on different direction, and so it's going to be deflected in 2 places. And on the left side is the light that is around 1.7 micron, and on 1.7 is the H band. Is the H band 1.7? Well, 1.7 micron, more or less. And the other on the right side is around 2.2 micron. And if you see here, the light is spread in different like curve lines. That is every line has a different wavelength coverage, and it goes from more blue to more red, and then these lines are more or less the same of this region, and then it's again blue and red. So you have what we call the H-band detector and the K-band detector here and here. What you're seeing is actually is an object that is resolved, spatially resolved. So what it looks like that is actually not fully on focus is this region, is actually on focus, but the object you're observing is resolved. So you have a spatial dimension that you can see in these images. And some other part of the spectrum, you see that, for instance, here, when some specific line are much more concentrated, you can see that there is light is actually perfectly, the image is perfectly sharp. And this, again, this V, it means that there is a velocity structure inside the object. So the more left you go, the higher wavelength, the more right you go, the longer wavelength. So this means that the same emission line or the same chemical element that's excited in this object is going two different wavelengths, because there's a velocity that's pushed the wavelength a little bit more red or a little bit more blue, depending on the region of the sky you are. I assume not many of you have seen a instrument of an 8-meter instrument telescope, and the crazy thing that these objects are big, like are really, really big. So this is IGNIRS 2 on the bottom that is mounted on the telescope. So this is our telescope. This is the Gemini North support of the mirror. So these entire things sustain the primary mirror, that is the mirror that collects the lights and takes all the images there, and it takes all the light there. And then on the bottom, there is that one that Zach was showing. The light bounces on the primary, goes on the top. There is a secondary mirror put on the top of the telescope that reflects the light down, and then enter here, and here where the instrument is. So here we will collect the data with this instrument is this. And so the size of this instrument is more or less the size of a person. And so it's just incredible that everything managed to work together, and we are moving quickly from one side to the other. Raja, you have a question?
I wanted to make a quick clarification because I don't know if the Modern High School International students use spectrographs in, let's say, their physics or chemistry laboratory. In case they don't, I wanted to just point out that when you look at a rainbow, and Lainani had a beautiful image of a rainbow behind her, when you see a rainbow, it's nature's way of producing a spectrum. And there, the drops of rain, water droplets in the air, are acting as prisms to split up the color of white sunlight into the 7 colors of the rainbow. What is above the human beings in this picture is the astronomical equivalent of a raindrop. It's an instrument that takes the light from stars, not the sun, faint light from stars. That's why it has to be big. It has to collect a lot of light from a faint star, and then it can break it up even more finely than a rainbow can. It can really break it up into thousands of colors. I just wanted to add that.
Mm-hmm. Yeah. Thank you very much. And this actually is a rainbow that nobody can actually see, because that goes in the infrared. So you observe redder than the reddest color that human being can see. So you have to imagine this is actually, for you, will look like you cannot see these colors. So it's just how incredible this instrument is. So coming back to this instrument, so this is the team that actually helped installing the instrument on the telescope. As you can imagine, it's not lifted by hands, but there is actually some crane that lift it up and put it together. Everything needs to be super precisely put together, and it needs to be at a cryogenic temperature. So it needs to be cooled down to minus 200 degrees. That's Celsius. I don't know if you're used to Celsius or Fahrenheit, or is approaching, going towards 0 Kelvin if you want to have that units of measurement. And to just show that after you do that, you take the first image, people are really happy and it's worth celebrating. So we have here, we have the picture of the entire team. They are all together that are like celebrating that for the first time, the light successfully moved from a star to our telescope, and we're able to detect what we expect to see. And if you can see here in the background, is actually the image that I showed you before as it came out from the telescope itself. So that's why there is this little hole where people can see here. What is incredible in this picture that there are so much expertise that is covered like a lot of things. There are like John White is here on Gemini North and is helping in the engineering side. He knows everything about the instrument, how to mount the instrument, how to dismount the instrument, how to fix the instrument when they break and everything. Then there is Jen Miller here, that is one of the experts that knows how to move the telescope, and like it's the same role that Denise has now in the control room. There is Avi and Emma that are the expert on the software side. So you want to make sure that there is every single component of the instrument communicate correctly with every single component that we have down on the base facility in Hilo with all the computers. There is Huey, that is the project manager, that is what is running and make sure that all of us coordinate together. This instrument has been sponsored by Kazi, that is the Korean Astronomical Society. Hi? Institute. That is part of their joining Gemini. They contribute, part of their contribution was given by delivering this instrument to the community. And all the members of the Kazi Institute are here. This is Chan, is the instrument PI, is the one that have the project in hands, make sure that everything was delivered at the instrument level. And this is Yewon that you will see here, that is super smiley because it was a long process. And I mean, when you commission an instrument, there is a lot of like hiccups and like bumps during the road. But that's why when you're right at the end, you're extremely excited about it. Coming back to this, I think here, that's what Raja was mentioning before. So what we have with this instrument, we actually create a rainbow that we cannot see. So it's a rainbow in what we call the infrared bands. And when you observe an astronomical object, you have three types of sources. You can see a star that has what we call the continuum. So you see like sort of like a uniform emission that goes through the entire rainbow without like many bumps up and down, just going like more or less flat. And then you have what you call absorption feature and what you call emission features. And when absorption and emission are they are caused by two different type of physical processes. But what you see here is that emission. So that means that there are specific elements that are excited at the right temperature, at the right density, and by the right radiation field, that the electrons pump up, fall down, and then you have the emission in specific lines. And so these are what they are highlighted here. And that's when you do science, these are the interesting part, because you can take, for instance, the H2 line or all this, the transition, and say, okay, if I know how much this emission come out, what is the ratio between the different transition of the same element, where is the location, then you can start to understand the physical component of this part. And so that's why we are really excited about this instrument, because this is a new unique capabilities that the Gemini North is going to have delivered to the community. And to make you how close we are to do that, as of tomorrow, we start the final stage of commissioning. So we are going to run from an observation from the beginning to the end and make sure that everything works properly. And then in July, we will going to offer the instrument to a restrict number of users to make sure that also external users can provide their feedback on everything going well. And then starting from September next year, we're going to offer it. If everything goes well, because you never know, if everything goes well, we are going to offer this to the entire community. And every single person in the world is allowed to ask, if they have a good idea, they can ask for this instrument. They say, okay, I want to use this Eigenstuhl instrument. I want to observe this target. Can you give me time? You write that in 2 pages. You send it to Gemini. A team of experts decide, read your proposal together with other people and decide which one is the best proposal among these. They rank it in order, and then they give you time if the proposal is worth observing. anything else? I think.
Emma, is there any chance you could give us an idea? Maybe you already said something about it, but of the science that's going to be performed potentially with this instrument? I noticed you showed a picture that had a bunch of letters and Roman numerals on it. Might that be interesting for science?
Yes, I think the expert here is Zach on the topic. So because Yvonne and I actually work on what we call IRS shift. So if it means basically that we're trying to look to the object the farthest possible from us. And as you can imagine, if a candle is brought really, really, really far for you, it's really hard to see. And so it's hard to use this instrument for our science because the object we want to observe are too far and too faint to be used with this. But this instrument is really great for, given that it's split the rainbow of the lights in that many different colors, is really useful for more nearby objects, for stars, and for objects that like, it's not naked eye object, but objects that are like clearly visible in the sky with a telescope. One of the exciting projects that people want to do is actually try to detect planets. And so what you observe as stars that is really bright, and then there is a planet rotating around the stars. And when the planet move around the star, you actually have variation of this line that I showed you before and variation of the flux. And then with this instrument is so precise that you can actually start to understand the physical property of the planet that is moving around it. Other capabilities are what I was showing before is a planetary nebula. So this what is called this like the an object like it could be a remnant of a supernova explosion. And what you have like this powerful shock that excite the gas that is around the star that exploded, and then you have this bright emission line and everything. And then this one of the other target is binary stars that I will leave the world leader on this argument that is Zach is on my side.
I wouldn't say world, but so yeah, I do a lot of stuff with binary. So in particular with Igrins, what you can do is kind of what the scientists who are taking the science on the program right now that we were looking at with the IFU, they kind of want to do that with another instrument that we have. But for Igrins in particular, what happens is kind of the same idea with the exoplanet, where you have two stars orbiting each other, and you watch and you take the spectra at different points in the orbit as it's going around the star, as the other star is going around the star. And effectively what happens is those lines shift a little bit. They go left, they go right, depending on whether the stars are moving towards or away from us over the course of their orbit. And you're able to map out effectively the orbit of these binaries in velocity space. And then by using that, you're able to go and get you're able to figure out a lot of the parameters of those stars. And so much like in the same way, you're able to do it for exoplanets. So a lot of the techniques that we're using for different aspects of science, you can apply to other areas as well. So I see Jamika has raised her hand, and I'll hand it over to her.
Thank you so much. Thank you so much, Zach and Emma. I just have a quick question. Let me lower my hand there. Just a quick question for Heywan. Heywan, so we saw you and the team image there with Igrins 2, and I'm very curious if you could share with us briefly, especially with the students here, a bit about your experience. What did it feel like to work with this international team and the success of having first light with Igrins 2?
As you can see in my picture, the Igrins 2 commissioning first light picture, I was very happy. So, and this is the instrument that built by Kashi team. the partner of the Gemini Observatory. And as I'm Korean, so I'm kind of very proud of them. And this is actually the first instrument they made by themselves for the first time. So it's really great for the Korean Astronomy and Instrument Society as well. And yes, I always happy with working with the international community and various peoples. So we're from Korea, Italy, and USA. So yeah, the Gemini Observatory is really the international observatory to work with. Diverse people. I like it.
As a follow-up, since I know there's going to be some testing tomorrow, Haewon, what's your role in tomorrow's tests along with Emma and the rest of the team?
You want me to talk? Okay. So this is transition phase. The Kashi instrument team, they bring the instrument to us. So we're trained by them how to observe with this instrument, how to check this instrument. We need to check the instrument health and the status when they are done with the commissioning. So we will closely work with the Kashi team to learn about the instrument to observe by ourselves. So we're very excited about this.
So basically, next week will represent the moment where the instrument moves from the ends of the builders to the ends of the users. And everything that can be, all the information that can be passed from one side to the other needs to happen this week. So it's going to be an exciting and exhausting week in front of us.
So how long has it been? When did Cassie start to build?
I think before COVID.
Right.
I think that's one of the crazy things with, as some of you may remember, 2019 and 2020, there were like some hiccups in your normal life, and apparently also in the building are really expensive, really complicated instruments can be like challenging. And there's been a lot of delay and a lot of instrument has been delayed, like you have problem. And I still remember one of the first meeting when there's been an apology saying that we're sorry that we are 2 weeks late respect to the scheduled time. And we were like, everyone was like, I think it's fine. So there's been like an incredible effort to keep everything into track and respect every single deadline that we set before the COVID-19 pandemic struck us. And so it's super exciting that this instrument is actually here, right on time, like a couple of weeks delay, but all the rest is on track. So kudos to the Kazi team.
Wonderful. That was amazing insights into IGRINs, and you definitely got us really excited. And certainly we hope to check in with you on future Gemini North sessions to see how everything is going. So thank you again, Emma and Haewon. Now, before
actually, could I ask a quick question to Emma and Haewon and possibly Zach as well? So before we let them off the hook. Just a quick question. So you mentioned, Zach, I think you mentioned that the science, at least some of the science case for IGRINs too. So some of the things that people are probably going to envision doing science on with observations from IGRIN 2 are similar to the one that's being taken right now with the GNIRS integral field unit spectrograph. And so I wonder if you could give a flavor of what differentiates IGRINs 2 from the capabilities that we already have here at Gemini North.
Yeah, so I think the biggest difference. I think the biggest difference, I mean, especially between GMOS and IGRINs 2 is in two ways. Number one, one's in the infrared and one's in the optical. There are a different variety of lines available. And at least for some stars, they can be brighter in the infrared than they are in the optical, so it makes them easier to observe. But then one of the bigger difference for, at least for binary stars and searching for those shifts in the wavelengths that I was mentioning earlier, is that IGRINS has a resolution of about, I don't know what the resolution is for the instrument.
45,000.
Well, for the GMOS IFU.
Oh,
What?
10,000? No.
45, it's probably like,
Yeah.
10,000-ish.
so it's a factor of 4 better. And so you're able to identify more of those lines and pick out more of those lines and be able to map out the rate, see smaller shifts in the lines versus in IGRINS 2 versus GMOS. So.
Great, thanks, Zach. And yeah, so right now we're using GNIRS as an IFU, and that has similar resolution, I guess, to the GMOS IFU. And so again, I guess the IGRINS 2 is going to have a resolution capability that well exceeds at least our current low resolution IFU capabilities in terms of resolution. We do have a new high resolution IFU, but even that, I think the maximum resolution is like 18,000. So still a factor of more than 2 better resolution with IGRINS 2. So, but it is a slit spectrograph, right? So you're not getting the full spatial information that you would get with an integral field unit, but you are getting much better, as you said, velocity resolution than we would with the integral field unit observations. So I get the feeling that they're kind of complementary in terms of science cases.
Yeah, I need to remind myself every day now that GNIRS has IFU capability, so I can't just say IFU, it means GMOS around here now. So
Yes, Emma and I spent a long time speaking of commissioning processes, and I think that was about 2.5 years to commission both the high resolution IFU and the low resolution IFU. So basically the entire time that Emma and I have been working at Gemini North, right? We spent commissioning. And so I think as maybe a month ago, we officially released the high resolution IFU to the community. So people can apply for, or did apply for, the 24B semester, which starts later this year. And there will be observations as early as July with the high resolution IFU. Currently taking the observations with the low resolution IFU. It's low resolution in the sense that its spectral resolution is not as high as the high resolution spectrograph, hence the name. But still, this is kind of at least what I'm used to, a decent resolution for a lot of science cases. And you have a fairly large field of view, so you can get, for example, this particular system that we're looking at. I think it's has a biconical outflow, so there's gas being pushed out from this star. It may be that it's a binary star, as Zach mentioned, and so you're able to see the kind of full picture around this star. Whereas if you just had a slit and you were just placing it on the star, you may not get, well, you certainly wouldn't get all that information, but you may not get the information that you want to, depending on the orientation of the slit. So you may have to take multiple orientations, or you may have to find a IFU that has very high resolution if that's what you need.
All right. So before we get back to the science that's going on right now in the Gemini Hilo Base Facility control room, which you can see right behind me. This is where Denise and Brian are. I'd like to just say again to the teachers and students here with us from MHSI, if you have a question, please feel free to post it in the chat. If you'd like to ask it, just ask it out loud. If you'll just raise your virtual hand. I believe you have microphones. I think I saw some of the teachers with microphones. Just raise your virtual hand. We would happily invite you to ask your question. So you can do that anytime. Okay, so now back to Zach. Zachary, so there are two roles going on here in the control room. We have Denise and Brian working together, but kind of working at two different aspects of observing. Could you give us some insights on those two roles?
Yeah. So where Brian is right now, that's where a lot of the astronomers and scientists here would normally sit. That's the observer chair, along with the SOSs. And so in particular, that's where we're in charge of the instruments and taking the science. So you have two roles here. You have the observer and the operator. And so the operator is in charge of the telescope and in charge of the safety of both the safety of the telescope and making sure the telescope is pointed at the right target and is guiding on a suitable star so that we can maintain where we are pointing in the sky. And then once that is done, then Brian is in charge of the instruments and making sure that the instruments take the data correctly. And so after every image, Brian will go and check those images and make sure they look okay. So for example, earlier when we had the instance of saturation on the image, he did the correct thing and checked with the contact scientist, who is the person who's communicating from Gemini with the person who proposed for the science, and making sure their programs are set up correctly in our systems. They were able to modify the program a little bit and make sure that it's not as saturated. And so now it appears to be going quite smoothly. And to just kind of give you an idea for this target about how long we're going to be here, I mean, it's pretty much from the beginning of the session and until now, we're still pointing at that target and taking data. And we'll be pointing at this target for pretty much the entire session today. So this is a long observation using short observation. So you're just taking, as you might remember, it was 40 exposures by 10 seconds, or 40 coads by 10 seconds for each exposure. And so and that is done over the course of the next hour or so over a couple of different wavelengths. So
just to jump in for a sec, Zach, so sorry to interrupt, but yeah, we basically started the beginning of the session taking a calibration frame. So this was this calibration star. And we do this to understand the absorption of the Earth's atmosphere to certain wavelengths of light. So we took our calibration star basically right as the session started, and we're going to take observations of this target in 3 different central wavelengths. So we're going to be looking at just red of human vision, and then further red, and then even further red, almost all the way to at least partway to the atmosphere cutoff. And so we have exceptional conditions tonight. And so this is why we're able to take these observations. They need very high spatial resolution. And we're achieving it. Well, we're not doing anything. Maunakea is giving it to us, which is wonderful. And that's part of the reason why there are many telescopes here. But the observation of this target will stay on for almost 2 hours. And then we'll go to a second calibrator source. So this is to measure how the Earth's atmosphere has changed in terms of its absorption properties over the course of that 2 hours. And the proposing team will use the observations of both calibrators to correct the scientific observations to remove the atmosphere of the Earth. So all of the calibrations that we take, I think Zach was mentioning this earlier, all the calibrations that we take is basically to remove anything associated with the telescope, with the instrument, with the detector, with the Earth's atmosphere, basically removing all the terrestrial aspects of the observations to get to the true astronomical profiles, to get the true astronomical information, so that one can then do science with that information. So if one attempts to do science without these calibrators, you get very bad answers and very incorrect answers, because there's absorption from the atmosphere, there's inefficiency of the detectors, there's inefficiency due to reflections of the light on different mirrors, and that can confuse, if you don't take appropriate calibrators, that can confuse the data that you get out after the interpretation of those data. So yeah, we're here until if the conditions stay steady. I mean, we're in really wonderful conditions. So we're in what's called image quality 20, which means that we only get these conditions 20% of the time or so. And if the conditions hold, we'll stay here all the way till 11:30 Hawaii time. So another 2 hours roughly.
Incredible. Absolutely incredible. This is, I'm just to have these wonderful conditions when just last week, I think what we had snow on Maunakea. It really does change a lot. And so it is wonderful to be able to experience pristine seeing and conditions for these observations.
Yeah, just to your point, Tanika, I actually went up to the summit as a tourist on Friday, and the winds up on the East Ridge, which is where Gemini sits, where one of the University of Hawaii telescopes sits, one of the Canada-France-Hawaii telescope sits. The wind speeds were in excess of 110 kilometers per hour, and that causes a lot of turbulence. And so the resolution that we got that night was roughly a factor of 5 worse than we're getting now. And that was just, what, 3 days ago? And I did see snow up at the top, so all the snow hasn't melted. So yeah, just dramatic changes over the course of a very short period of time.
Amazing. Okay, so I was just before Brian added that last bit, I was going to check in with the teachers and students there at the Modern High School International to see if there were any questions or comments. And indeed, yes, I see that there's some questions. So if you will, I'm not sure which is the image. Yes, I will ask you to unmute yourself and ask your question, please.
We can hear you. Yes.
Yes, I can hear you.
How to balance using such
Wait, can you repeat your question right in the microphone so that we can clearly understand you? Thank you.
Yes,
Your audio is very low. It's very soft.
so the question is, how do you balance making these telescopes and making?
I think they're typing into the chat. That would be
Yes,
best.
okay,
And
wonderful.
we'll repeat your question for the whole group so that others can hear it too.
Absolutely.
While we're waiting for you to type it in, what you were describing, Brian, with calibrations, I've come to thinking of that as the essence of data reduction. When you reduce raw data, you're really removing instrumental and atmospheric signatures from the astronomical one. How do you balance making using these telescopes and maintaining the environment? That's a great question.
Yes, thank you for that question. Zach, Brian, Denise?
So the person that would be very wonderful to answer that question is Leilani, actually, and she, I think, had to go to sleep, which is totally reasonable since her job is mostly during the day. I can take a shot at answering the question, but I am not. I don't help to build the telescopes, and in fact, we have a summit crew that goes up there to the summit of Maunakea every single day. They are very well versed in the ecological consequences of them being up there and of the telescope being up there. And so they receive a lot of training on what to do and what not to do. The summit is also, there's a steward organization, which is led by a set of rangers that are here. And those rangers are extremely dedicated to making sure that the ecological impacts of humans, both tourists and astronomers, up on the top of the Mauna is minimal. The day crew, we have a lot of protocols in terms of, there's a lot of material that's shipped up to the summit that's potentially damaging to the environment around. And so making sure that we take very good care of that material, that we use it in the way that it's supposed to be used, and that we dispose of it in the way that it's supposed to be disposed. That's all critical to our kuleana here, our responsibility. So I think we do this very carefully. And anytime a telescope is obsolete, so no longer used up at the Mauna, and that's happened before, and it's happening currently, we make sure that the site for that telescope is returned to its natural state. And so we have one telescope that's has just been decommissioned. So this is basically, it's stopping observations. This is the Caltech Submillimeter Observatory. And so they're slowly taking the dome structure off of the summit, and then they'll remove all of the associated infrastructure and then return the summit to its native state. So it's a very careful balance. It's a very, as Leilani very clearly outlined, it's a very fragile ecosystem, and Hawaii in general is a fragile ecosystem with humans and all the activity that's happening here can have very damaging impacts. And so we have to be very, very careful in our approach. And so there's a lot of incredibly dedicated people that do that. I don't personally work on the summit that much. And so my responsibility is down here at sea level mostly. But we're apprised of, how careful everybody is up at the summit, to make sure to put summit activities, the ecology to the forefront, not prioritize astronomical observations, but rather, the summit being a place that everybody can enjoy and commune with for generations to come. Hopefully that helped answer the question somewhat.
I think that was brilliant.
I'd like to chime in a little bit, please, here as well.
Please.
Again, Brian, as you said, Leilani is the one with the, with the cultural expertise, certainly. I'll give you a slightly different, it's not opposed to your perspective at all, Brian, but a slightly different angle to this. I've worked for over 30 years with the city of San Jose to control light pollution in the city, so that the observatory and astronomers can do their work in California. In these ways, the observatory is on the side of preserving a pristine environment from the standpoint of light pollution. Light pollution is one of the ways in which we're damaging the environment, and dust, light pollution, these are, vehicular pollution, these are things that are damaging to the environment, but they're also damaging to astronomy. So often observatories restrict traffic on mountaintops because they don't want it overrun with lights. They don't want it overrun with vehicles kicking up dust and vehicular pollution. So there are some ways in which observatories actually side with trying to maintain the pristine nature of the environment. I just wanted to add that.
Thank you, Raja. Thank you so much for that additional perspective. And I believe that Zach, is that you sharing your screen with us? Yes. Okay.
There we go. There's the mute button somewhere on my end.
Okay, great. Catch us up on the science, and then we have another questions from the students, which we'll get to right after your update.
Yeah, I mean, I'm just putting it up there for as we're having these discussions and answering questions to show what we're seeing as we go through. So periodically you'll see the screen update as we get new data in. But right now this is live data being taken using GNIRS. So that's it there.
Yeah, so I'll just mention that we're absolutely rolling along. So our instrument, our sensors are all measuring that the conditions are just as beautiful as when we started, which is great because this program requires them. And as Zach mentioned, this is real data coming out now. This is of this star, which may be a double star. It may have a gas and dust envelope around it. And so this image right here is the integral field unit data coming out. And in fact, so this is on source, what we call on source. So looking at the star itself. In about 10 seconds, we're actually we just moved off to what we call a sky frame. So we basically went to a location where we don't think that there's a source. And because the infrared sky is so bright, we actually have to use the observation of the source and the observation of the sky. So you see all those beautiful photons from the star went away, and we're left basically just with the spectrum of the night sky. And so we'll subtract those two. They're very close in time, just about, about 5 minutes separated in readout. The atmosphere changes in the near infrared on timescales of 2 to 5 minutes. And so you need to take these exposures in sequence in order to get a good difference image. So now we're back onto the source, and we're taking another about 5-minute observation. We'll continue to do that. I think we have one more sky frame after that. Then we're going to take some calibrations, which will be internal to the telescope. And then we're moving on, not to a different target, but in fact to a different central wavelength. And so this program is looking at a very large wavelength baseline. And this is to get a number of transitions from different elements and different molecules, both in the photosphere of the star and then the surrounding gas and dust. So if everything works well and conditions are going well, this will actually be quite boring, and it's wonderful when astronomy is, at least when you're observing, it's boring because that means usually things are working very, very well.
Yes, you've mentioned in previous sessions how exciting it is when it's boring because it means all is moving along smoothly. So we're excited for that to continue. Okay,
I'll
so
just sorry, Jamika, I'll just mention before you go to the question. But one of the strengths of the Gemini Observatory, which was highlighted by Emma and Heywan and Zach, is our versatility. We have incredible suite of instruments. And we also allow scientists from all over the world to do what's called trigger, which means that they see something up in the sky, a supernova or some other transient event, and they can activate, so they can basically request an observation. And that level of that request, how urgent it is, depends on what we assign as the scientific merit of that observation. So if we believe that the scientific merit is quite high, they can request us to actually abandon the observations that we're taking now and move on to another target. And so there's some thought that perhaps tonight there will be one of these requests that come in. We'll get an alert here in the control room. You'll probably hear it in the background. It'll say attention, target of opportunity. And then Denise and I will scramble to understand, well, how quickly do we have to take it? Do we have to abandon the observations that we're taking now and move on to somewhere else? And so that is kind of a white noise that exists for Gemini at all times because we are incredibly versatile. We can switch instruments very, very quickly and we can move the telescope to a different part of the sky very quickly. So I just want to say, yes, boring, but any second things could dramatically change, and that's kind of the fun of astronomy. Well, one of the many things that are fun about astronomy.
Fantastic. Wow. Okay, so we'll be listening out for that notification for a potential target of opportunity. How often does it happen where you do get this TOO, target of opportunity, that's triggered where it's so urgent that you have to abandon the current observation?
That's not super common. So usually we can finish our observations. It depends. I think it's going to become more common over the next year or so as the Rubin Observatory in the south comes online. So this is going to be looking at large swaths of the sky every night, and there'll be a lot more transient events that people will notice and then ask us to look at. This has happened quite a bit this semester, these targets of opportunity, but it actually happens during the day. So people realize, oh, there was a, supernova, a star blew up or something the previous night. They want to observe the following night. And so they will they will ask during the day. For example, I am a contact scientist on one of the programs, and so I'll help them set up their observations during the day so we can kind of do it leisurely. And then as soon as the night starts, if their target is up, then we immediately go to that target and take the observation. So a lot of times it's, in between when people ask for it and the time we're actually observing it, maybe 6 to 8 hours roughly. And that's a nice amount of time to get observations ready, make sure that we have everything exactly the way that we want, because telescope time is very expensive. And then get on to the target and take the observations that the person wants.
Thank you. Okay, so question here from one of the students. What is the most difficult task when it comes to managing such an advanced telescope?
Well, Zach, can I kick it to you? Because you've actually done more roles at the observatory than I have.
Yeah, I'd have to say probably all of us here are either science fellows or astronomers or scientists or SOSs. I would say on my end, it would have to have been QCing. So QCing is Q coordinating. So as Brian mentioned earlier, Gemini is a Q observatory. So we take in 100 or more proposals each semester, and where we have to observe them over the course of the semester in their given conditions and or potentially during the timing windows that they desire. And this is different than other observatories where you might yourself just have, say, a night that has been assigned to you, and you go that night, and whether or not the night is great with great weather or terrible with terrible weather, that is your night and you don't get anything else. And so with Gemini, though, we have this queue system where it gives you a little bit more flexibility in terms of conditions. So if your target's not observed tonight, for example, it could be observed tomorrow. And every single day, there's somebody at the observatory who is putting together that schedule. for different weather conditions. So you go through and you make a weather plan that is made for the conditions that we have right now, which is great. Or we go make a plan for conditions that are terrible, like it's super cloudy or the seeing is 15. And every single day we have to do that. And then, it could take a little bit of time or it could take a long time. It's taken me from, maybe as short as 2 to 3 hours a day to as long as 6 to 8 hours a day. And then, you are in charge of the queue for that entire shift that you're on. And so if, for example, a rapid TOO were to happen right now, and we are still in IQ 20, then it is entirely possible that the current QC, the current queue coordinator, could get a call from Brian and Denise saying, hey, what has priority here? And that could happen at any time during the night. It could happen at 8 p.m. or it could happen at 5 a.m. So I would say that from my experience is the most difficult task. In my limited experience, is the most difficult task when it comes to managing the telescopes. It's just you're in charge of the queue system for or the queue for a whole week, and you have to make the plans, and you are responsible for it. And you have to remember the programs and which ones need to be observed tonight versus tomorrow and that kind of stuff. So I would say that is my experience. I don't know whether Brian or anybody else has any difference of opinion.
Well, I haven't had the pleasure, Zach, of being a queue coordinator. I will start shortly. So your words were very encouraging in that regard. Well, I just want to say that, I think, I agree. I think that job is incredibly difficult, and it's basically a 24-hour job, which is crazy. You have to be not only, be on call all night, but you're also, we have our operations meeting every morning, and that is now run in part by the queue coordinator. You give an idea of what science was observed the previous night. You give people an idea of what is coming for the next night. And then you're spending all day planning. And then again, you're on call the next night. And I guess these are roughly like 10-day shifts. So it's you basically go into a tunnel and you come out 10 days later, as far as I understand. But I will mention, so we're on the kind of operations side. We're, trained scientists. There are tons of observatory staff here, including some that I mentioned earlier, which go up to the summit every day. The summit is not an easy place to work. It's 4,000 meters. There's 60% of the oxygen that there is down here at sea level. There's no infrastructure. And you have to do, heavy physical work up there at the summit 5 days a week. And if something goes wrong over the weekend and it's pretty catastrophic, you have to drop your weekend plans and go up to the summit as well. And that requires about 45-minute drive outside of where we are in Hilo up to an acclimation point, waiting about half an hour to 45 minutes at the acclimation point, then driving, another half an hour up to the summit, doing whatever work you need to do, and then coming all the way back down. So that is incredible. And you have to think up on the summit, which is, I have observed from the summit before with the Subaru telescope, which is also on the summit of Maunakea. And it is definitely not easy to think up there. And so, you're dealing with huge pieces of equipment. You have the fate of the entire observatory in your hands when, they're for example, refurbishing our mirror, or they're doing an instrument exchange. So they're taking off one instrument, putting on another instrument, as they're going to do with IGRINS 2 tomorrow. And they have to be lucid and, aware and physically capable at all times. So that's, we have a tough job down here, but we do it at 300 feet above sea level with our coffee in our hands.
if I can chime in, is actually the crazy part of this job is it's always like our final goal is to get on sky and do what Brian is doing now, is get them some of the most spectacular data every astronomer always want to have in their hands. And to have this running is actually is a lot of people working all together, coordinating and having everything right in place by 7 in the evening when we start the nights. So there are situations where you have to keep working until the last second to make things, to have everything ready in the right spot at the right time. There are routine things you do every day. Our software support and our IT support reboot the machine every morning or run some tests every day. The people that collected after the data collected are put on archive. That is the way that the user interact with Gemini Observatory. And there are people that check that everything that's written in the archive is up to date, correct. We report there the condition of the sky. We report there everything that happened during the night. Every morning at 9:30, we have a sort of a group meeting that includes everyone at the observatory. That's see what's happened during the night. If there is any any problem with any instrument, we need to solve it during the day. If it takes more than one day, there is someone in contact with the Q coordinator that was Zach was mentioning. Then needs, if one of the instruments has a major fault and cannot use during the night, you have to fully restructure your night based on the fact of the instrument you can actually use. So every single of the person that is here is important and has a different role, with the only goal to take the data during the night.
Yeah, what would you guys say? Maybe roughly 50, 60, 70 staff working here in Hilo.
Yeah.
Make sure that everything's running up correctly, and then the equivalent number of staff at Serapatron. So
Yeah.
roughly 150 staff to run 2 observatories.
And that does seem like a lot of responsibilities, and I appreciate the different perspectives that you were each sharing. So Emma, Zach, Brian, also Denise, Heywan, how much training does it take to be flexible and versatile in managing the various roles that you are able to to take on here at Gemini North?
It's an extremely good question. It really depends. So not always you have the luxury of proper training. There are situations where, for instance, to learn how to do QC or to learn how to do some of the things, it requires a lot of time, and there is a person that passes the information to the other. And we have also for observing, we have observing training. So people that know how to observe spend some time to train the next person. So then we are more or less everyone at the same level of learning how to do this. But there are situations where you sort of have to improvise yourself in the position. If something happens during the day that you don't have experience with, you actually, I don't know how to say properly, you have to suck it up and work around it and try to find a solution for the problem. So it's a different level. There is a lot of times we have training, we learn, and a lot of times we learn while doing. And there are incredible people here that have knowledge. I cannot say that some of the people at the observatory knows everything, and they're our spiritual grandfathers here, or grandmothers, depending of the gender. And we know that when something happens, we can always turn to them, and they will be super nice and super knowledgeable and tell us what's happening. And that's how it works. And then we learn, and hopefully in 30 years from now, we'll be seen in the same way that we actually know what we are doing, and the younger generation will refer to us for that.
Unless you're GNIRS point of contact and
Yes.
everybody is working on proposals and GNIRS breaks and you're like, what's going on?
Yeah. That can also happen.
sounds like a very specific incident.
Yeah.
I don't recall that. I blacked out.
Oh my goodness. Okay, so I see we have more of our wonderful scholars here entering questions here in the chat. Thank you so much. Keep those coming. We have about 20 minutes left. And we're so pleased that you're still with us and that you're engaging with us with your questions and comments. One thing I'd like to throw out to the teachers and students, and you can feel free to answer in the chat, is first, what grade levels do we have with us? And after the grade levels, what background do you have in, maybe astronomy and physics and math that's a part of this kind of field of study? Yes, take your time entering the questions, no worries. Okay, so we have questions from some of the economic students. All right. So considering the equipment used in astronomy are certainly money intensive. That's a good way to put it. They're definitely money intensive. How do you allocate the investments in different areas? Wow. And how does your mission contribute to the island's welfare? Ooh, brilliant questions. So first, how do you allocate the investment in different areas for the equipment needed for astronomy? It's open to everyone.
Big offsets, Denise.
Yeah.
I mean, I guess I could start. I could say that we have funding agencies. So Gemini is funded by NSF, and at certain points there may be proposals for a certain type of instrument, or there may be a team that wants to build a specific instrument and then bring it out to Gemini as part of our visitor instrument program. They may go and get funding through the NSF through a competitive process. They apply, there's a science case, technical case, it goes through peer review, the best program is selected. And that's a more general viewpoint on
I'm just reacting.
how more general, maybe not viewpoint, of general explanation of how instruments are selected.
Didn't
Here,
realize you were still.
Gemini has some funding for instruments, but not a lot, and it really depends on what the partners in particular want for the observatory. So as you mentioned, Gemini is an international collaboration. So everything we do, we go through all of our different partner institutions and figure out, what are the top science interests of each partner, and try and mesh those so that our instrument suite allows for a complete examination of those science goals.
I think it's all. Okay, good. Back on source. HPen.
Anyone else want to add to what Zach shares there? And I'm going to add a chat link to just a list of the the various partners that Gemini has, because I think, of course, when you're talking about funding, that of course it's important to collaborate with all of the vested their various interest groups, partners, of course, to allocate those funds. Is there like a time when everyone gets together to discuss kind of the best ways to use the funds, and like a budget meeting, or is that done by each kind of partner country, and then
No, Jessica, something's wrong.
it comes together after? I'm just curious, because that seems like a lot to manage.
What? I think it's the board meeting. So, I mean, we're having the board meeting here actually in 3 weeks, 2 weeks, something like that. 2 weeks. No, 3 weeks. So the board is made up of representatives from each of the different partners. And so they get together and decide and kind of go through what the observatory is doing, what they would like changed, potentially budget information. And so they meet twice a year, once in Hilo and once in La Serena in November, and down in Chile. And so that, I mean, and they probably meet throughout the year, but those are the meetings at least that we're aware of. So
I want to add a little bit on the contribution to the welfare of the island. So if the big island is a special place on the planet, and there is the major contribution to the economy of the island is given by tourism, by the military, by healthcare, and by cutting-edge research. And cutting-edge research includes astronomy. And there is not only Gemini on the island, so we have this Gemini, Keck, Subaru, some millimeter array, IRTF. Maybe if everything's confirmed, the TMT in the future. So there is like thousands of people that work on the island to make everything works. And there is an effort to have the local community to contribute at different level. There is an effort that contributes to have people from Hawaii. So there are not that many STEM industries on the island, and astronomy is one of the few of them that is actually here and can bring people back in case someone from Hawaii got a degree on the mainland and then will come back in Hawaii as like an engineering, as an astronomer, as a software specialist. There are a lot of things we can offer you. And so we are here because this is one of the best mountains in the world where to do astronomy. And we are here because we also try to help the community, or to be part of the community as much as possible.
That's absolutely right, Emma. I'm so grateful that you shared that perspective, because it's important to realize the critical role that the observatories play and the economics of the Big Island, along with all those other aspects that you shared as well. And as Emma was naming the different observatories on Maunakea, I've dropped a link there so that you can check those out for yourselves and get a bit more understanding of the other observatories that share the summit region with Gemini North. So in our last 12 minutes, I do want to again encourage you all to keep up those questions and comments. Please, no worries. We're happy to continue having your questions. And while you're doing that, things have changed on the screen. Zach, what are we looking at? Emma?
Well, if Brian wants to describe what's going on, because I have lost track of what's happening.
Oh, yes. When Brian has a chance.
Yes.
Yeah, so I'm here with our venerable contact scientist for this program, Heywan, and we are it's a rare pleasure to have the contact scientist in the room assessing the data at the same time, and we're trying to understand. We saw a little bit of funkiness in one of we observed this target for about an hour and a half, and then we wanted to just make sure that we moved the telescope just a little tiny bit to get it recentered for the next set of observations. And we didn't like what we saw in that observation, but the subsequent observations look fine. And so we're just trying to assess, are the conditions still as good as required for this this program? So this program has like some of the strictest conditions possible. And so we don't want to be taking observations if we're not achieving what we believe is required for them. It does look like Jamaica. It does look like we're not saturating, which is great.
Great. Go ahead.
But we're not totally sure that we're getting exactly what we want. That's yeah.
Oops.
Yeah, that's
Yeah,
what
it
that
was
was the first one.
already.
Oh yeah, okay.
Yeah. Exactly this. Do you tune with the RTEP?
Yeah. So right now we're just looking at the first science image of the sequence. So there's our target, and I'm going to do a radial profile of that target, and we're getting through the IFU, we're getting about 0.6 arcseconds. So that may not be sufficient for their program, even though P2 is reading 0.34 at the moment. Well, we're not guiding, but it was the last time it made a measurement. So it's 0.5 arcseconds in the V band, and we're taking observations in the H band right now. So it should be much better seeing in the H band. And for some reason, we're not seeing it now. One thing is we don't know that this is a point source. We don't know it's a point source in H, right?
Can you look at this is the yeah, it's not point source, it's really kind of extended features around. This is diff data.
Yeah, and this is a AOFED.
Yes.
Yeah, okay. So it should be actually about full width half max of like 0.6. Oh, okay. Okay, so we got tricked. We're actually resolving it. So it's a star, which should be a point source in general, but it has a dust envelope around it. In fact, I guess a decade ago that it wasn't observable even in the optical. Like there was no evidence of it, but it was super bright in the IR. And so I think this thing is like, what is it? So it's like 10,000 times brighter or more in the infrared than it is in the optical. And we're observing in the infrared right now. And so it's just, we're actually going to the longest wavelength observation of the sequence. And it's, I think we have to go to our minimal exposure time. So it's 0.2 seconds just to be able to observe it, just so it doesn't blow out our detector. So I think we're good, actually.
Yeah, since this is not point source, yeah, this is fine. That's reading.
We got a P2 spike, but yeah, we're heading pretty steady at 0.4.
The position look fun.
Yeah, I don't know what happened. Maybe we were moving still or something like that.
Oh, you took the image during the movie?
We didn't move though, actually.
Yeah.
But it was we were in offset position, and it was moving by itself because we went from off guiding. Oh, we went from off guiding and pushed it back. Oh, that's exactly what it is. So we're off guiding, I pushed it back to center,
Center,
but it was
and-
taking the observation as it was pushing back
Yeah.
to center.
Okay.
Because we were like a couple, what was it? These are like offset by
100.
arc and a half, right? So so it takes a little bit of time to move that.
Yeah.
Okay, so that's why.
Mhm.
Phew, no coma. Okay, so that was an observer error. That was me.
I figure out how to fix the.
But no damage to the science. Everything looks wonderful actually right now.
Great.
So we're just finishing up this sequence, and then we're going to go to one more sequence in a slightly bluer, still well in the infrared, so well past the range of human seeing. So we have one more sequence, and then we'll actually finish this program. So we'll take a calibration observation at the end, and then we will be done with this program. So in fact, we've finished 2 programs this evening. One with the MAROON-X instrument, which is one we didn't get a chance to talk about tonight, but is featured in many other Shadow the Scientist sessions at Gemini North. Looking at I think it was at Neptune or something like that. I can't even remember. And so, but anyways, at a fairly close by object. And then this one is also fairly close by object, a star in the Milky Way.
It's pretty amazing to experience live that kind of problem solving right with you, just essentially, again, eavesdropping, exactly why Raja started this this initiative, to really see what it's like to deal with issues as they come up, when things are going smoothly, but also when sometimes there are a few bumps in the road, as Emma said earlier. Amazing. And as you said, it's rare to have the actual contact scientists with you to consult.
Totally, yeah. And this is one of the wonderful things with the observatory life and astronomy in general, actually. I would say science in general, by and large, is that everybody is kind of going for the same goal here at Gemini. We're here to make the best use of the time that we have available. And so everybody is working towards that goal. Everybody's working as a team. People will wake up at 3 a.m. If something breaks, we can call them and, they'll get up. We don't generally drive to the summit at nighttime. But first thing in the morning, they'll drive to the summit and they'll take a look, inside of the instrument. It's just incredible to work in an environment where it's so international, as Heywan mentioned, so many different partners. People apply from all over the world with their ideas, and we're the stewards here trying to realize those ideas as best as we can. And again, Maunakea is a very wonderful partner in that, because it gives us many nights of very wonderful conditions. It's, I think, without a doubt, the best place in the Northern Hemisphere to observe with these telescopes. And tonight is absolutely evidence of that, because it's very few spots on Earth that you'd be able to do the kind of observation that we're doing right now.
We are glad to be able to shadow you all as you do it. Okay, in this last 3 minutes, we have a question. What is the most fundamental element for manufacturing a telescope like Gemini North? Wow. What's the most fundamental element for manufacturing the kind of telescope that you all use? I'd imagine there's quite a bit that's actually fundamental.
Gosh, I don't know. Silver is a big one for us. So silver is what our mirror is coated with, and it has very good optical and infrared reflectivity, which is why we use it. We're actually one of the probably the most infrared, one of the most infrared optimized telescopes on Maunakea and in the world. And so silver is one that is very, very big for us.
I have another one. That's glass. Of getting very high quality glass that doesn't have any bubbles in it or anything like that, because ultimately glass is the substrate on which the whether it's silver or gold or aluminum, whatever the coating is, has to sit on a substrate, and that glass has to be super smooth to optical wavelengths. I know mechanical engineering is a big part of it, so availability of the right metals, and you want metals that don't have a high coefficient of expansion and contraction. Those things are. I've had the privilege of being a faculty colleague of Jerry Nelson, who was one of the world's foremost telescope builders of the modern day, and it's just incredible to watch these things from the sidelines. I'm also, like Brian said, not a telescope builder, but those who do are do a remarkable work.
Yes,
And
absolutely.
sorry, Jamika, I was just going to chime in with one other thing.
Sure,
When you look
please.
at this, these images remind me of something that may not be apparent to the students who've connected from Modern High School. You look at these two buildings if you look at the panel in the lower left, you see these two buildings. They look like normal sized buildings. But when you see a human being standing next to them, or you see a car next to them, you realize that each of these buildings is the height of a 15 or 20-story building. It's not, these are huge, gigantic structures. So to build them is no small feat, no pun intended.
Roger, you always intend the pun. You always intend the pun.
I can confirm
Very
that.
strategic with them. Oh, okay. We're at the end of our session, but we do have another question that I'd like to have someone address generally. How does the recent geopolitical tensions affect your cause? So how do politics affect the running of the observatory, whether it's local or international? How do you deal with that as a staff?
Well, that is a very complicated question for the end of our session.
What
And
a
it's
great
an
question.
incredibly important one as well. Geez. Okay. So, well, I would say local politics play a huge part in what we do up on the Mauna. If people here in Hawaii don't want the telescopes, if there's a movement against, let's say, deprioritizing science, and in particular astronomy, then that can certainly affect what we do up on the Mauna. And there has been recent debates in the last couple of years surrounding what voices are heard in terms of the stewardship of Maunakea. And it was concluded by the state and codified in a bill that was passed by the state that there should be more voices that are heard and responsible for the stewardship of the Mauna. And so the University of Hawaii was the main steward for a very long time up on Maunakea, and they have given way to a stewardship committee, which sources cultural practitioners, lineal descendants, so native practitioners, but also sources points of view from other disciplines, from ecology experts, and there's representative from Maunakea observatories. And so this large group of people with very diverse points of view and very diverse backgrounds will form over the next several years the vision for what Maunakea will be over the coming decades. But Gemini being a telescope that is invested in by 6 partner countries, we are our funding and our mission is very much dependent on the political directions of each of the partner countries. And so, for example, there was a new president elected in Argentina that may not be as interested in supporting some of the science that we do here. And so that's something we certainly have to think about as we move forward in terms of our funding, our responsibilities, and what our plan is for the next, at least several years, if not more.
Brilliant response, Brian. Brilliant. And with that, we are 3 minutes over our time, but I would like to say thank you so much again for the privilege of shadowing the observing team at here behind me at the International Gemini North. Again, I want to thank our very special guests who are with us. Not only the additional hosts who guided us through the session, Zach Hartman, and our special drop-in guest, Leilani Losi, but also, of course, Emma and Heywan for that amazing, the amazing insights into iGrins too. And we certainly look forward to checking in with them on progress, and wish them the best